Good evening, everyone. My name is Harini. I'm a PhD student from Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. Currently, I'm doing NPTEL TA-ship for the course Watershed Hydrology, offered by Professor Rajendra Singh from IIT Kharagpur. In today's lecture, we will be discussing about few of the topics, very few topics, like reservoir sedimentation and one of the hydrological model HBV and few more minor topics, and then we will be solving few questions related to this and also few questions related to previous topics. So this will be the last lecture for the current course. So if you have any doubts, you can ask during the session or you can mail the questions. So let's start with what is HBV model. It's one of the hydrological model. So sir has demonstrated this model in his lecture. You can see how the setup of this model is done and what kind of how the format of the input file should be and how the output files format will be and how the plotting is done for the outputs. So first we will be discussing about HBV model. So the full form of HBV model is hydrological balance, pattern balance, and okay. So it's a Swedish model, and it is a hydrological water balance model. So what is hydrological model and hydraulic model is like, suppose if you are having mostly in hydrological modeling, what will happen is like if we have a rainfall amount, we will know how much is the runoff on the surface and what will be the stream flow. All these details will get when the inputs are runoff. When the input is precipitation. But in case of hydraulic model, the routing will occur, so we will know how the water flow will occur at each locations rather than only at a particular location. Okay. So the routing will take place and also we can have a 2D plot of the models like how the inundation or flooding is happening due to the rainfall event. All this information you can get from a hydraulic model. But here we will be discussing about hydrological events. So in this we are generating runoff when the inputs are precipitation, temperature, and some other more meteorological variables. So it is developed by SMHI, which is Swedish Meteorological and Hydrological Institute in 1976. Okay, so it's basically a conceptual model and also it can be fully distributed or semi-distributed model. So if you remember, we have discussed about what is a lump model, what is a distributed model in the previous classes. So if for a catchment, we are having for this entire catchment, we are giving single time series as input for precipitation or temperature or any other variable, and you are getting output also a single time series. So it's like a averaged data for the entire catchment. Okay, so that kind of models are called as lump model. But in the case of distributed model, generally we will give inputs as gridded in the format of grid. So at each location, a few locations we know the input variables, and we are giving that as input into the hydrological model, and we are generating output at each of these grid points. So that's why we will get an idea of how the spatial variation of any hydrological or meteorological variable is in the basin using a distributed model. But in case of lump model, you will get an averaged idea. Like for this entire basin, we'll have only one single time series of stream flow as output. Then we won't understand how it is varying spatially, right? So we only get an average idea of how the basin is overall performing in generate runoff from rainfall. So here the data that is required are precipitation, temperature, mean monthly temperature, and potential evapotranspiration. These are the inputs that we will be giving into the model to generate runoff. So mainly this model is widely used for generating runoff. Okay. So simulate runoff. So in this model, we have four modules. Each of these models we will be discussing in the further, and also we will be discussing about the model structure of the HPV model. So if you see here, we can see the modules of the HPV model. We have four models that those are like one is snow module, soil module, response function, routing module, routing. So if you see, we will not understand what it is exactly, so that we will look into it inside it. So snow model is nothing but suppose we have precipitation and temperature as we are giving as input into this model, then we'll get an idea of how much of the snow is covered in the area and how much of it is melting which is producing as runoff. All this information about the variable snow. Okay, you'll get information from snow module. And next we have soil module, for which the inputs are potential evapotranspiration, precipitation, and snow melt. Using this, the outputs will be based on the current precipitation or snow melt condition. We will know how much of water is infiltrated into the soil, and based on that, we will know what is the actual evapotranspiration. So if the soil is dry, the actual evapotranspiration will be zero. And if it is wet, we will have a evapotranspiration equal to potential evapotranspiration. So the outputs based on these inputs like potential evapotranspiration, precipitation, and snow melt, get an idea of how the actual evapotranspiration is occurring in the basin, and also what is the soil moisture, and then groundwater recharge. Okay, so here we will only in this module only the upper layer of the soil we are concentrating how much of water is infiltrating into the upper layers of the soil, and because of that how much of evapotranspiration is occurring. All this information we are getting. But in case of response function, that is third module, we'll get an idea of how the groundwater recharge and potential evapotranspiration is occurring. So here mainly they are concentrating about the groundwater structure. So whatever water that the soil is observing, how much of it is going into the groundwater recharge. Okay, and also how the groundwater level is varying. That is, water table level is varying, and in turn, whatever water is flowing into the deeper layers of the soil. Okay, we know that in turn this also will come as runoff and in longer time scale, right? So as a base flow or any other flow, base flow, interflow. So all these flows will finally come and recharge the stream flow. So all this we will be getting an idea of what is the groundwater level and runoff in response function. And the fourth module, last module, is routing routine, where runoff is generated, and using the runoff as input, they're simulating the runoff. So suppose if we have a runoff like this, so using the routing function, what they're doing is they will actually the runoff might not be like that because of all the land use, land cover, and evapotranspiration, everything, infiltration, infiltration loss or depression storage, everything, all these interception losses. Because of this, the runoff might not be that. So there will be a transformation function which we will be applying on the runoff that is generated in the third module to obtain the simulated runoff. Okay. So generally in case of simulated runoff, the peak will be reduced and also there will be a time lag. So here, next we are discussing about the model structure of a HBV model. If you see here, we have, as we have discussed, there is a snow routine where from precipitation data and also temperature data, right? What is the snow melt? Everything we will get an idea. Suppose how we are getting information about based on just temperature. So if the temperature is greater than 0 degrees or any minimum threshold, what they are saying is there will be snow melt occurring. So because of that, snow melt runoff will be generated. So that's where the main important inputs are precipitation and temperature. And based on the precipitation that is occurring, we will have a soil routine. So how much amount of water is infiltrating into the upper layers of the soil. And then we are checking about how the groundwater routine, that is how much of water is going into groundwater recharge. And finally, from all these buckets, how much of water is returning back into the stream. So this might be clear picture for you. Based on the precipitation and temperature, we will know the snow cover, snow melt, everything, and based on that, how much soil, what soil is getting, uh, in how much water, sorry, how much moisture is getting infiltrated into the soil, upper layers of the soil, and then it will go for the saturated zones like groundwater table, how much of it is recharging, and how the fluctuations of groundwater table is, and all that. And from there, also the base flow or base flow is occurring, which is finally contributing to the lakes or storage structure or rivers where the stream flow is occurring. So first, we'll be talking about the first module, snow routine. So snow routine, it is based on traditional degree approach. So here, what they are doing is accumulation of precipitation as snow will occur when the temperature is less than a threshold temperature. Keep. Okay, so whatever precipitation that is occurring, and if the current temperature is less than this threshold temperature, then that means the precipitation is coming in the form of snow. Okay, so and when does the snow melt of snow starts? If temperature is greater than this threshold temperature T. Okay, so they also have a formula for this. Snow melt is equal to CF max of T minus TT, units are in mm per day. So CF max is the degree day factor which will range from 1.5 to 4 per degree Celsius per day. Okay. Then if temperature is less than TT. This means the whatever snow that is melted, it refreezes again. Okay. So when we have to calculate the refreezing snowman is equal to CFR into CF max T minus T. So CF max is decay factor and CFR is refreezing coefficient, which is approximately equal to 0.05. Okay. So whatever all the precipitation that is simulated to be snow should be multiplied by a correction factor SFCF. Okay, in this case, okay, all precipitation simulated to be snow should multiplied by a correction factor. So one of the main advantage of this HBV model is also that it has a snow module where you can have an idea, we can apply in the snow covered regions also. So many of the hydrological model doesn't consider snow module. That's why they are having this disadvantage. But also, whatever the steps that I'm discussing currently, you don't have to do anything. This is the software is coded such a way that all this is done. All this can be is calculated by the software itself. You just have to give the inputs in correct format and also the correct values of the inputs you have to give. Okay. So after snow routine, the next one is soil moisture routine. So all these I'm discussing just because you have an idea of how the software is doing the calculations. Okay. So the soil moisture storage is represented as SM and it is the key variable in this module and generally it will range from 0 to FC. Generally FC we call it as field capacity. Also here if you see we have one more variable SM by FC. So since the soil moisture storage will vary from 0 to FC, SM by FC will vary from 0 to 1. So it is an index of soil wetness in the basin. So if the SM by FC value is 1, then we can say that the soil is wet. If it is 0, then the soil is very dry. So based on the this ratio value, we can know the wetness of the soil in the basin. Then it determines how much of water becomes recharge and eventually runoff and how much remains in soil. So how do you think one simple index can give us an idea about all these things is that suppose if the SM by FC value is 1, then we know that the soil is fully saturated. So that means whatever the rainfall that is falling will mostly go as runoff, right? So we have an idea of runoff and if the soil is completely wet and how much we know we will get an idea of how by using some formulas related to groundwater recharge and groundwater flow, we have like Darcy's equation. We can know how much of groundwater recharge is happening. And also based on this FE value, if it is full, that means the soil is completely wet, right? So all this, so that's where we get an idea of all these three variables if you have a value SM by FC value. So as I've discussed, if the soil moisture uh, depletes, then what will happen if the soil is wet? Then potential evapotranspiration will occur. But if the soil is dry, an actual evapotranspiration will occur, which is less than potential evapotranspiration. Then we have recharge by LP is equal to SSM by FC whole power into. So FC is the maximum soil moisture storage. Maximum soil moisture storage in mm. LP is the soil moisture value above which PT actual evapotranspiration reaches potential transpiration evapotranspiration, that is also in mm. And here beta is the parameter that determines related contribution of runoff from rain and snowmelt. Okay, so if you see here, we will know from this figure, like based on the contribute fraction of rain and the y-axis is fraction of rain and snowmelt, x-axis is soil moisture. And based on the soil moisture values, we will know how much of contribution of rainfall or snowmelt is giving it to soil moisture storage or upper groundwater recharge. Okay, so if you see as the soil moisture is increasing, then the fraction of rain or snowmelt contribution to soil moisture storage is also increasing, right? And after this point, we are saying there is a groundwater recharge is occurring. So if the soil moisture level is more than this point, then groundwater recharge will occur. And below this, there is only soil moisture storage. That is like only the top layer of the soil. There will be moisture stored. Okay. Then we will be discussing about the response routine. So in response routine, the main important uh, assumption is it follows simple linear reservoir condition. Okay. So that means the outflow is a linear function of storage that generally we give as relationship as K into S. Okay. So in this case, in response function, if you see, we have two buckets and three runoff components. See here, there is one runoff component, second runoff component, third runoff component, and two buckets that are present in the response routine function. Okay. And if you see, once the water is flowing from soil moisture, it is reaching the groundwater zone. And in this groundwater zone also, storage zone also, we have an upper zone and lower zones. And in the case of upper zone, there is a threshold kept, okay? Threshold parameter UZL. So if it is more than that, if the storage in the upper zone is more than this threshold value, then only there will be a runoff occurring from the first component, okay, here, Q naught. If the storage is not above this threshold, then the runoff will occur only from the second component, that is Q1. Okay, and from the first bucket, that is upper zone, the water is flowing into the lower zones by process called percolation. And in the case of the second zone, there is no upper limit, and whatever water that is coming into this lower zone will contribute to the runoff as Q2 equal to K2 into S1 center. So generally the Q2, that is the runoff from the second bucket, will never exceed the percolation capacity of the soil, and because SLZ can never exceed percolation by K2. Okay, so is this part clear, or if you have any questions, you can ask me in the middle. And also we have routing routine, that is the fourth module, in which we use a transformation function. Like I said, suppose if the runoff that is generated after the third module is this, then we have a transformation function to produce a hydrograph after the routing is occurring. So generally the peak will be reduced, and also there will be a timeline that is occurring. So in this they use a transformation function which the generated runoff of a one time step is distributed on following days using one free parameter max bus, which determines the base signal equilateral triangular wave function. So basically it transforms the hydrograph. Okay. That is generated after the second module. It will get transformed using transformation function. We generate the final runoff hydrograph. So then for any model, we have multiple parameters. So here we will be here. This is the list of parameters in the HBV model. So first we have vegetation zone parameters. Generally for any catchment, if we are going for distributed, since it has a distributed or semi-distributed modules, we can classify the basin into maximum of, I think, three vegetation zones. And for each zone, we have to give the values of these parameters. Okay. Suppose TT is what is the threshold temperature. Like we have discussed in degree day factor. The threshold temperature is important to know how much of snow is melting and whether the precipitation is occurring in snow form or rainfall form. All this we will get an idea based on this threshold temperature. And we have CF max, SFCF, all these first four are related to snow module, and then CFR, CWH, all these parameters from soil moisture routine also we have. Okay. Then we have model parameters related to catchment, like what is the percolation capacity of the soil, and what will be the upper threshold for the upper basket in the in the response routine, and what is the K1, K0, K1, K2 hydraulic conductivities, all these kind of questions. Okay, we have to give an values for all these parameters when you are setting up a model. So initially we don't know what will be the values of this model. So what we will do is basically based on the knowledge of the basin, we can give some values for this parameters. And once you calibrate the model, then you will get the finalized values for these parameters, which will give us the good runoff that that will be for the basin. Okay. So the steps involved in the modeling are: first we need input data. So this input data should be in the format that they have mentioned, like in the text file you have to write in multiple columns, you have to give the precipitation, temperature, all these variables details. And then we give some parameter values randomly, mostly based on some idea about the basin. You can assume some values for these parameters. So that basically we are setting up the model. And then we do model calibration. So we have discussed this, what is calibration also based on the observed, suppose here we are calibrating the model based on runoff. So we have observed runoff data, and also whatever the model that is generated, that runoff is called as simulated runoff. And we will be using some objective function like minimize the mean square error or minimize NIC, all these kind of functions we will use such that the error between the observed and simulated runoffs will be reduced, and accordingly the parameter values will be changed when you are calibrating. So once you get an optimized parameters, that means where the NSC value is high, or where MSC means where error is less, they those parameters are called as optimized parameters, and those parameters we will be using further for stream flow generation. Okay, so in case of HPV model, this model calibration can be done manually, that is by trial and error. You can keep changing the parameter values and generate the runoff and see how the mean square error or any other function that you are considering is changing. And then if a particular set of parameters are giving us the a less minimum MSC value, mean square error, then we consider that as optimized parameters. Okay. But going manually is very hectic. You need high computation because you have to run multiple times. Or we have another option called Monte Carlo simulation in HPV model. What it will do is, this will, once you activate this Monte Carlo simulation, it will automatically calibrate the model and you will get the optimized parameter by minimizing whatever function you are giving. If you are choosing MSC, mean square error, or NSC based on this objective function, it will give automatically the optimized parameter values. And then what we will be doing is model validation. So, in what is the main difference between calibration and validation, as we have discussed earlier? So, in case of calibration, we will look at the data, observed stream flow data also, and we were trying to get the optimized parameters. In case of validation, using the optimized parameters that we obtained in calibration stage, we will be running the model for the next time period, which it hasn't seen. And then we will get the stream flow simulated, and then we will compare with the observed data. So we will have an idea whether we are doing an overfitting or not. If the model performance performs well both in calibration and validation phase, then it is a good model. If it performs well only in calibration phase, then the model is overfitted. So that's how we will get an idea. If it is performing poorly in both the cases, we have to do optimization such a format that you get better optimized parameters. Okay. So after this, once you get validation also, we use in model calibration and validation itself, we use different criteria to assess the fit of simulated runoff to observed runoff. So that means, like, I have told you, like, what do you mean that how do we say the simulated runoff and observed runoff are matching well? So for that we use different criteria, like I have told, MSC, NSC, or just by a visual inspection. If you do draw both the time series, okay, And if there is a huge, suppose this is our observed time series, and this is the simulated one. So do you think both are matching? They are not matching, right? So the simulation from the model is not good. So if suppose if it is like this, then we say that it is almost able to capture the pattern, but there are at few points it's missing the to capture the data, right? So that's how by just by visual inspection also we can know. But if we have two models which are almost performing good in visual inspection, then we will go with this performance measures like MSE, NSE, and all. Okay, like accumulated difference. Statistical criteria. And in this HPV model, we have an option of graphic option, which will give an idea of how the simulated runoff and observed runoff, it will automatically plot once you activate that option. So like we can also see how the ground soil moisture is also varying once you activate the different options in graphics. Yeah, from this, so this is how we do modeling. These are the steps involved in the modeling. Any kind of modeling that you are taking, these are the basic steps that are involved. So then what are the applications of this HBV hydrological model? So first one is if the sometimes what will happen is we are recording the data using stream gauges. In some cases they might be malfunctioned or they are not recording the data, so there will be gaps in the data. And if suppose there is a flood event and the stream gauge is not able to record after that event, okay, we don't have any more data till today. Then we can use these hydrological models to extend or fill the gaps in the data, extend the data, or extend it historically or for future also. And if we have what is the forecast values of these meteorological variables like precipitation, temperature, we can know the forecast of the stream flow also using these models. So the application of this model is to extend the runoff data series or for filling gaps. Next, for water balance studies. So if you see, it gives us an idea of what is the soil moisture, what is the runoff, all these variables are given. So in the water balance equation, we can use this data and study about other variables also. For runoff forecasting, this will be helpful in flood warning and reservoir operation. Next, to compute design floods for dam safety. Next, to simulate climate change effects. So if you remember, like we know we have different scenarios. Suppose if the temperature is increased by 1.5 degrees or 2.5 degrees, we have different scenarios. We cannot actually experience them in real life. So we can what we can do is once we have a calibrated hydrological model, and since we know how the precipitation and temperature will be behaving at that kind of scenarios, using those as inputs, we can understand how the runoff is getting affected because of climate change in the basin. So, or soil moisture, all these kind of things we can analyze using a hydrological model. Okay. So, the next minor topic that we will be discussing is land capability classification. So in this mainly we are trying to look at the capacity of the land surface to support various uses such as like natural plant growth, wildlife habitat, artificial crop cultivation, and human habitation. So if you remember, if you know, like we know that all kinds of land doesn't is not suitable for like so suppose if you take uh, what are the most suitable land for agriculture? We have some type of soil types which are more suitable for agriculture, and few soil types like which are mostly consisting of rock. It is most likely not suitable for agriculture, right? So based on this kind of data, we have the Indian government has done the based on the land classes. It has divided the whatever the lands available in India into 8 categories basically, and given us an idea if the land is falling in category one. So, what is it suitable for? Whether it is suitable for agriculture or wildlife or for human habitation, or if it is falling in class two, like that, they have given us an brief guidelines. So, using if we follow those guidelines, we will have a better results. So if you are going with agriculture, if it is falling in class 8, it is not suitable for agriculture, then we will not use those land for agriculture. So then we can prevent losses and all. It's okay. Capacity of land surface to support various uses such as natural plant growth, wildlife habitat, artificial cultivation, and human habitation. So based on that, we are having multiple classes based on capability. Okay, it is determined by slope, soil type, slope, depth, and erosion conditions. So the main purpose of this kind of classification is to it helps us in defining land conservation problems and for possible treatment. Suppose if we know a particular land in our area is falling in land in a class where the erosion is more. So we know what is the problem with that land. So we can apply some treatment measures like growing trees will prevent the erosion. So like this, we can apply some mitigation measures for the treatment. So another purpose is that it results in high integrated watershed management on a long-term basis. So then the classes are the classification is done by All India Soil and Land Use Survey. So now it is also called as survey. Sorry, now it is called as Soil and Land Use Survey of India, Ministry of Agriculture in Farmers Welfare. So if you see here, we have totally 8 classes in land capability classification, and here first four clauses are suitable for cultivation, and the last four are like from 5, 6, 7, 8. They are unsuitable for cultivation. And if you see here, and in each class they have a description. Like suppose if the class is assigned as one, generally the slopes generally within 1% and also very good arable land with no specific difficulty in farm. So class 1 is best suitable for farming. So if you go for class 8, it has a very steepest slope. So we cannot do agriculture here. The slope also exists 25% and it is only suitable for wildlife. So, so like this, based on the class type, we will have different types of descriptions that they have given, and based on this we can know whether it is suitable for cultivation or for wildlife. So suppose if you see classics, they are saying the slopes are ranging to 18% and it is well suitable for grazing and forestry but not for cultivation. Okay, so suppose if you take class 3, the slope is varying from 3 to 5%. It is moderately good for cultivation, but the specific attention should be given for erosion control. So based on this guidelines, we can do better uh, in giving us the production. Okay, there are also subclasses related to this. Suppose if we are saying class 1, sorry, class 3E, then it means it falls under class 3, okay, which has a slope of 3 to 5% and moderately good at cultivation, and it has a risk of erosion or past erosion damage has occurred in this kind of land. So based on these subclasses, we'll get an idea of, suppose if it is a W, wetness damage or overflow can happen. And if it is S, soil roots or limitation. So the roots of the soil cannot penetrate more than a particular depth. So on this C is climatic limitations. Based on the subclasses, we will also get a better idea about the kind of land that is there in the field. So the next one is and suitability classification. In case of land suitability, the fitness of a given type of land for defined use is generally estimated. So it has four categories. First is orders. It reflects the kind of suitability. So basically, it has only two groups. One is S suitable. Another one is N, which is not suitable. So if we are checking whether the land is suitable for agriculture or not, and you go for order. If in the case of order, if it is S, then it means it is suitable for agriculture. If it is N, then it means it is not suitable for agriculture. Then upon further dividing this orders, we have classes, which reflects the degree of suitability within orders. So here if you see, there are multiple classes like S1, S2, S3, N1, N2. So S means it is suitable, N means not suitable. So if S1 means highly suitable. So here if you see the description, land having no significant limitation to sustainable application for a given land use or any minor or only minor limitation. So since here we are talking about agriculture, so if the land class is S1, that means it is highly suitable for agriculture. But if it is S3, it is not well suitable for agriculture, but we can use it. Uh, but we will have a RCBA for sustained application of the given use. Okay. So if it is N, then it is not suitable So if it is N1, that means it is currently unsuitable, but you can apply some measures so that it can be suitable for the agriculture for in future. If it is an N2 case, it is permanently unsuitable. But if you are applying any mitigation measure or any measures you are taking to improve the nature of the land, nothing can work and it won't be suitable for agriculture at all. So upon further dividing the classes, we have subclasses which reflects kind of limitation or kind of improvement required within classes. So here if you see there are different subclasses like C, T, W, N, F, S. So here it will give us the limitation. So if it is falling under S3 class and T is the subclass, that means it's marginally suitable for agriculture with limitation that because of the topographical limitation, maybe because the slope is very steep. Okay, so there that means that is one of the topographical limitation that is having for the land. And further dividing the subclasses, we have units which reflect minor differences within subclasses in the required management. Okay. So the minor differences in subclasses is noted in this, and generally these minor units are used for farm planning level. These different These differ from each other on production characteristics or in minor aspects of their management requirements. Okay. I hope this is clear. What is land capability classification? What is land suitability classification? If you have any doubts, you can ask me or you can message in the chat box. So if there are no questions, we'll go for reservoir sedimentation. So in the case of reservoirs, what will happen in rivers? Generally, water will be flowing. When it is flowing, it will take some of the water, some of the sediments from the soil, from upstream to downstream. So then if there is a reservoir, the water is flowing in the river. Okay, from upstream, it carries sediments to the downstream, but you have a reservoir in between. So what will happen? All these sediments will get accumulated in this. So if this keeps getting accumulated, the capacity of the reservoir to hold water will be reducing, right? So that's why this reservoir sedimentation is a huge problem in the reservoir maintenance. So rivers transport huge amount of sediments shaping features like riverbanks, deltas, alluvial fans, braided rivers, lakes, and reefs. Okay, so reservoir construction impedes sediment flow downstream causing sediment accumulation in the reservoirs. Despite varying sediment rates, all reservoirs eventually lose water storage capacity as sediments occupies water storage spaces. Okay. According to International Commission on Large Dams report, the global average sediment rate is around 0.96%. The average sediment rate. So the impacts of this is the life of the reservoir will be shortened and there will be reduced storage capacity of the reservoir, which will decrease the ability to produce hydropower, hydroelectric power, and also it reduces the ability of water. Since the water storage capacity is reduced, so we don't have enough water holding, so the water that will be used for irrigation will also be reduced. So we have different forms of sediment transport in rivers. The first one is bedload, where the most of the sediments are coming from the bed of the river channel. Then suspended loads. So this one is like the sediments will be floating on the surface of the water. And there is another one, wash load, which is a suspended fine materials but not from the bed material. Okay, if you see here, we have different classification: wash load, suspended load, and bed load, right? Okay, wash load, suspended bed material load, and bed load. So in this wash load and suspended bed material load are both suspended load. And this case, in case of bed, it won't be a sediment suspended load. And the based on the particle size, the wash load are like bigger compared to the other two types of loads. Okay. So then we will be discussing about graph efficiency. So it is the ratio of total sediments retained by reservoir to the total sediments entering into the reservoir. There are different factors that will influence the trap efficiency, mainly the retention time of runoff and sediment particles, settling visibility, velocity of the sediment particle, dam characteristics. Dam characteristic, what is the type of the dam, position and size of outlet, number of outlets and dams, etc. This will be the, so if it is the case of sediment velocity, settling velocity of sediment, what is the incoming sediment characteristics, the grain size, because settling velocity mainly depends on the grain size of the sediment, flocculation, density, and if when you are talking about retention and time of runoff and sediment particles, mainly reservoir characteristics and inflow characteristics are the major factors that influence the trap velocity. So to estimate the trap velocity, we have different equations and empirical curves. Okay, first one is Brown's curve. So if you see here, based on different sizes of the um, sediment, we have different types of curves, and based on the area feet per square mile of drainage area, we have different values. Just by getting these values, we can get the traffic, sorry, trap efficiency for different sediments. So the equation for that is E is equal to 1 minus exponential times of minus AB into L by H into WS by Q. So where L is the length of the reservoir in meters, WS is the settling velocity of sediment, H is the mean flow depth of reservoir, Q is the mean flow velocity of reservoir, and AB is a quotient whose value is generally fixed as 1.055. Okay. And the next one, we have Churchill's curve. In this, we have multiple equations where E is equal to minus 20 plus 0.95 SI whole power 0.63 by 7500 plus SI whole power 0.63. So this is when SI is greater than 6 into 10 power 4, which is a 2.5A. So you have to see this 2.5A curve, that is blue shaded curve. When SI value is greater than 6 into 10 power 4, you have to get the values of the corresponding trap efficiency from the blue curve. Okay. So another one is minus 1.1 plus 0.25 into log SI. This you have to apply in case of SI is less than or equal to 2.6 into 10 power 4. Then one more condition we have is ERS is equal to 1 when SI is greater than or equal to 2.5 into 10 power 8, that is 2.5 precondition. So that is this red line. Okay. So here we don't know what is SI, right? So SI is sediment index, which is calculated using R by P. R is the period of retention and V is the mean velocity. R is C by I, resident velocity, period of retention is calculated using C, that is capacity of the reservoir divided by the average daily inflow. And V is when as I by A, which is V is the mean velocity, I is the inflow rate, A average inflow rate, A is the average cross-section area, and A is average cross-section area equal to C by N, that is capacity of the reservoir by length of the reservoir. So totally SI can be calculated by C by I whole square by L. Okay. So ERES is the reservoir trap efficiency, and SI is the sediment index, C is the capacity of reservoir at mean operating load, I is the average daily inflow rate, R is the period of retention, V is the mean velocity, A is average cross-section area, L is the reservoir length, mean operating level. So then we have one more curve called Broom curve. You can get directly from this empirical curves also the values. Or you can use the equation E is equal to 0.00085 plus V by VW whole power 1.1 by 0.0085 into so plus V by VW whole power 1.1. This is for V by VW greater than 0.003. The VW is the average annual inflow volume and V is the storage volume of reservoir below line through bed level and upstream pump. So here only we have two parameters V and VW, so it is most widely used. But the problem is that it is only established using a normal ponded reservoir, so it might not be applicable for all kind of reservoirs. Okay. So, is there any questions related to these topics? Reservoirs, sedimentation, or land capability, land suitability, and also HBV hydrological model? So, there are no questions. Then let's proceed to some questions, multiple choice questions, and also some problems related to these topics. So first one is how many modules are there in HPV model? So if you remember, we have discussed about four modules. One is snow module, soil moisture module, then then we have I think response routine and then routing routine. So in total, we have four modules in HPV model. So HBV hydrological model can be used as fully distributed, semi-distributed, empirical, and the fourth option is fully distributed or semi-distributed. So remember we have discussed that can be used as fully distributed or semi-distributed hydrological model. So the next one is snow routine modeling in HBV hydrological model is based on option A, traditional degree day approach, option B, temperature index method, option C, energy budget method, option D, none of the above. So if you remember, in snow routine modeling, we have discussed about traditional degree day approach, and all these other methods are also used for snow routine only, but these are not used in HBV hydrological. So the next one is potential evapotranspiration across wind. Option A, soil is dry. Option B, soil is wet. Option C, soil moisture does impact evapotranspiration rate. Option D, thermal. So if you remember, when the soil is completely wet, then whatever evapotranspiration that is occurring will be equal to potential evapotranspiration. If it is not wet, if it is dry or it is unsaturated, semi-saturated like that, then whatever evapotranspiration that is occurring is equal to actual evapotranspiration. So the next question is, how many number of buckets are used in response routine module of HBV hydrological module? So if you remember, we have in response routine module, we have two buckets, upper and lower. And also we have three runoff components, Q0, Q1, and Q2. So there are two buckets in response routine module and three runoff components. Then the next question is, what is the applications of HBV hydrological model? First option is to extend runoff data series. Option B is for water balance studies. Option C is for runoff forecasting. Option D, all of the above. So we have discussed that all these three are the applications of HBV hydrological model, which will be extending the runoff data series or filling the gaps in the series. And also we can use it for water balance studies, because we'll get an idea of different variables within the basin using the HBV hydrological model. And also using the forecasted input data, we can generate the forecasted runoff also. Next one is which of the following best describes the objective of land capability classification? Option A to determine the market value of land. Option B to assess the agricultural potential and limitations of land. Option C to identify the geological composition of land. Option Option D is to evaluate the aesthetic appeal of the land. So basically, we are trying to assess the agricultural potential and limitation of the land. Because if you see land capability, we have classes from 1 to 8. Okay, in that we are majorly discussing about how the land, what kind of land is suitable for cultivation, for human, for wildlife, etc. And also what are the limitations? Like if it is class 3E, then there is a erosion problem associated with that land, particular land. So the option is B. Next question is which class in land capability classification represents land with the highest agricultural potential? So as remember from we have classes 1 to 8 in the land capability classification, and as we go, as first four are mostly suitable for cultivation, and last four are not suitable for agriculture. And among that, the agricultural capability of the class this land decreases as we go for higher class values. So if we say class 1 is most suitable for agriculture. Next question is in land capability classification, class A typically indicates. So also the table also. So if you see in this table, they're asking about class 8. So the class 8 has the steepest slope, which exceeds around almost 25%. And also it is only suitable for farming. That means it is not suitable for agriculture, for forestry, for grazing purpose also. So yeah, so the land use is most suitable only for farming. That is option. Then yeah, the next question is how does trap efficiency relate to sedimentation in reservoirs? Option A, higher trap efficiency leads to increased sedimentation. Option B, lower trap efficiency decreases sedimentation rates. Option C, trap efficiency has no impact on sedimentation. Option D is trap efficiency helps mitigate sedimentation by capturing sediment particles. So the answer is option D. The trap efficiency generally mitigates sedimentation by capturing the sediment particles. So the next one is the questions related to estimating the trap efficiency using Churchill method. So the Churchill method follows a formula using the sediment index. So first we have to calculate the sediment index value. So sediment index is calculated by C by I whole square by L. So the question is a reservoir has a following dimensions L equal to 25,000 meters, mean depth that is H equal to 20 meters and mean width W equal to 300 meters. The reservoir just upstream of the reservoir, the river just upstream of the reservoir has a depth of H naught 5 meters and width W naught of 100 meters. The discharge is inflow is 500 meter cube per second. The settling velocity is 0.1 mm per second, and the chassis roughness quotient CZ is 65 meter over 0.5 by second. So they are asking us to calculate the traffic efficiency using Churchill's method. So first we have to do is we have to calculate the sediment index. For that we need capacity of the reservoir, inflow and length of the reservoir. So capacity of the reservoir is calculated as length into width into depth So that is 25,000 into 20 into 300, which is equal to 1.5 into 10 power 8 meter cube. So inflow rate is given as 500 meter cube per second and length of the reservoir is 25,000. So SI is equal to C by 8. That is 1.5 into 10 power 8 by 500 whole square divided by length of the reservoir is 25,000. So once you calculate it, the value will be 3.6 into 10 power 6. Okay. So since it is greater than, this value is greater than 6 into 10 power 4. So it falls under 2.5a condition. So for that we use E is equal to minus 20 plus 0.95 SI whole power 0.63 by 7500 plus SI whole power 0.63. So this equation we will use for this particular condition. Okay, so minus 20 plus 9.5 into 3.6 into 10 power 6 whole power 0.63 by 1500 plus 3.6 into 10 power 6 whole power 0.6. So the value will be 0.61 once you calculate this. So the option is option B. So then next for same input data, they're asking us to calculate the trap efficiency using Bruns method. So in Bruns method, the trap efficiency formula is 0.00085 plus by EW whole power 1.1 by 2.0085 plus E by VW whole power 1.1. So first to calculate V is the storage volume of the reservoir. It's calculated using L by multiplying length into width into depth. So 5,000 into 20 into 300, that is 1.5 into 10 power 8 meter cube. And VW is the annual average inflow volume. So we have inflow. This we have to multiply in time units. So it's in second for annual average, right? So for 365 days, in a day we have 24 hours. Convert that into seconds. We have to multiply it by 3,600. So we'll get 1.57 into 10 power 10 meter cube is the average inflow volume at annual scale for the reservoir. The rest is calculated as 0.0085 plus 0.5 into 10 power 8 by 0.57 into 10 power 10 or power 1.1 by 0.5 plus 0.5 to 10 power 8 by 1.57 into 10 power 10. So once you do calculations, the answer will be equal to 0.42. Option C. Then the next question is also same, but using Brown's formula, we have to estimate the trap efficiency. So in Brown's formula, the equation is E equal to 1 minus E expo minus EB into EB into L by H into WS by U. Okay. So AB is we know quotient is fixed as 1.055. Length of the reservoir is to 25,000 meters, and height of the flow depth of the reservoir is given as 20 meters, and WS is the settling velocity of the sediment, which is given as 0.1 mm per second. That is equal to 0.01 meter per second. Just multiplying by 10 power minus 3, you get in meter per second. Okay. And then U is the mean flow velocity of the reservoir, which is estimated by Q by V into H. Okay. So inflow is 500 meter cube per second. So width and height are 300. So in that we get the average flow velocity in reservoir 0.083 meter per second. So E is estimated as trap efficiency is represented as 1 minus e power minus 1.055 into 25,000 by 20 into 0.0001 by is 0.083. So once you do the calculation, final value is 0.794. So that is option A. Then, from here we will be looking into few questions from different modules, like from week 1 to week 11. So the shape of the rising rim of the hydrograph depends on. So to remember, the hydrograph usually looks like this. And the shape of the rising rim means this part of the reservoir is mainly dependent on strong characteristics, and the falling limb of the hydrograph depends on the basin characteristics. Right. So the answer is option B, strong characteristics only. Then the next question is a triangular direct runoff hydrograph due to 6 hours storm in a catchment has a time base of 100 hours and a peak flow of 40 meter cube per second. So the hydrograph would look like this. And this they're saying is 100 hours. Peak flow they're saying is 40 meter cube per second. And the area of the catchment is 180 kilometers square. They're asking what is the peak flow for a 6-hour unit hydrograph. So that means that here it's a direct runoff hydrograph. So first we have to calculate the runoff value. So runoff volume is equal to the area of this hydrograph. So half into 40 into, so 100 it's in hours, but the discharge is in meter cube per second. So we have to convert time also into hours. So that's why I'm multiplying this with let me share the screen again. So, okay. So to convert the time in from hours to seconds, we have to multiply by 3,600. So that will be equal to 72 into 10 power 5 meter cube. So now that we have runoff volume, we have to find out runoff depth. That we can get by runoff volume by area of the catchment. So 72 into 10 power 5 by area of the catchment is in kilometer square. So I'm multiplying it with 10 power 6 to convert into meter square. Okay. Then we'll get as 0.04 meters. So multiplying by 100, we get in centimeters, that is 4 centimeters. So for 4 centimeter direct runoff hydrograph, we have a peak volume of 40 meter cube per second. For 1 centimeter unit hydrograph, what will be the peak hydrograph? So that is 40 into 1 by 4, that is 10 meter cube per second. So that's option A. So option A, 10 meter cube per second. So the next question is for station X, the maximum 1 year rainfall 25 years per period is 100 mm. The probability of 1 day rainfall equal to or greater than 100 mm at station X occurring at least once in 15 successive years is. So probability of rainfall equal to greater than 100 mm can be calculated as 1 by T. T is where T is the return period. So it is 1 by 25, that is equal to 0.04. So probability of not receiving a rainfall of magnitude greater than or equal to 100 will be 1 minus P, that is 1 minus 0.04, 0.96. Okay. So here they are saying what is the probability that rainfall at a station will be greater than or equal to 100 mm at least once in 15 years. So if we are considering that the distribution is binomial, then R comma Q equal to P. NCR e power R into Q power N minus R. So at least once in a year is better. What we will do is we will say 1 minus probability of no rainfall greater than or equal to 100 mm in 15 successive years. Capital. So that means that is 1 minus. There is no rainfall occurring. So that is, so probability will be Q and it is not occurring for 15 years. So power 15. 1 minus 0.96 whole power 50. So once you do the calculation, final value will be 0.458. Option A. The next question is the initial infiltration rate is at a capacity rate if the rainfall intensity is. So if you remember, the infiltration capacity of the soil will be a decreasing curve with time. Infiltration. And if the if the rainfall intensity is less than the capacity, infiltration capacity, then the infiltration that is occurring will be equal to rainfall intensity itself. So if the rainfall intensity is more than or equal to this capacity only, then the initial infiltration rate will be equal to capacity rate. So the option is option D. Rainfall intensity when it is equal to or more than the infiltration capacity of soil, then initial infiltration rate will be equal to capacity rate. So the next question is, a catchment has an area of 150 hectares and the runoff rainfall ratio is 0.4. Due to a 100 mm rainfall over the catchment, runoff at the catchment outlet lasts for 10 hours. The average runoff period is. So here, the runoff by rainfall is 0.4 and the rainfall value they have given it as 100 mm. So therefore runoff is equal to 0.4 into 100, that is 40 mm. And the area of the catchment is 150 hectares, right? So the volume, runoff volume is equal to 40 into 10 power minus 3 to convert it into meters, and to area. Since it is in hectares, you have to multiply with 10 power 4 to convert into meter square. So the answer is so 60,000 meter cube. Okay. So now that we have we have a runoff volume of 60,000 meter cube. They are saying that it is lasting for 10 hours. So the average runoff rate will be equal to runoff volume by time. So 60,000 by 10. So that is 6,000 meter cube per hour. So this option is not the correct answer. And 6,000, since it is an hour, to convert into minutes, we have to divide it by 60. That is 100 meter cube per minute. Okay. So the answer is option C. So then the last question is calculate the following NDVI ratios and comment on route. So the option we know that NDVI is calculated using NIR minus R by NIR plus R. So where this represents the reflectance in near infrared region and R represents the reflectance in red band. Okay. So for first one, NDVI is equal to NIR is given as 0.55 minus R is given as 0.08, 0.55 plus 0.08. So once you do the calculation, the answer will be 0.7. Then since the 0.74 is above 0.1, then it is above optimal. That means there is no drought. Okay. Next one, NDVI is equal to 0.45 minus 0.4 by 0.45 plus 0.4. So the answer is 0.067. So 0.06 lies in this range, which means it is a near normal drought. That means there is no severe drought that is occurring in the region. So here we have an optimal condition where we have sufficient water, more than sufficient water. Here we have normal rainfall occurring, so we don't have any drought as person. So, in today's topics we have this. In today's lecture we have discussed about how what are the modules involved in HBV hydrological model, how do we set up the hydrological model, and also land classification based on suitability and capability. And also we have discussed about the reservoir sedimentation. So also we have discussed some topics related to previous lectures also. So if you have any doubts related to this lecture or previous lectures, I can answer you. So if there are no doubts, can we end the session? You can send a mail of your questions, the mail as well. Okay. Thank you for listening.